Welcome back to Very Ordinary Differential Equations. In this lecture, we study solutions to higher order Euler equations. In general, an Euler equation is one where you have a sum of constants times powers of x times derivatives of y, where the power of x matches the derivative of y. Now, this equation can come in a non-homogeneous version as well, where the forcing function on the right isn't zero. Terminology will vary from place to place. In many sources, only a second-order equation of this form is called an Euler equation, and we have studied solutions to those before. However, the techniques for solving second-order equations generalize very quickly and nicely to these higher-order equations, so I like to call these Euler equations as well. So here is our general Euler equation, and we're going to perform the same substitution that we did in order to solve a second-order Euler equation. We're going to let x equal e to the t, and then we're going to transform this into a differential equation where t is the variable. The chain rule is going to be our governing principle. So dy dt is the product dy dx dx dt. So let's see how the chain rule and the product rule are going to help us compute higher derivatives of y as a function of t. For the first one, we simply say that dy dt, according to the chain rule, is dy dx dx dt. dy dx is what we've notated as y prime. dx dt is e to the t, because recall that x is e to the t. If we divide both sides by e to the t, we can solve for y prime equals e to the minus t dy dt. Now, in order to take another derivative against t, we would say that the second derivative of y is d by dt of d by dt of y. Up in this line here, we solved for dy dt as y prime e to the t, so substitute that here. Now we're doing d by dt of this, so we're going to use the product rule. First up, we would have y prime times d by dt of e to the t. Of course, that's just e to the t, so y prime e to the t, which is accounted for in the first product here. By the product rule, we would also have to take d by dt of y prime times e to the t unchanged, which is accounted for right there. We could also say that dy prime dt by the chain rule is dy prime dx dx dt. We're simply applying the chain rule to y prime as a function of x. So its t derivative is its x derivative times dx dt. Now, dy prime dx is just y double prime, the standard second derivative of y as a function of x. And as remarked already, dx dt is e to the t. So then we can say, going up to this line here, d squared y dt squared, we've already determined it to be e to the t times this sum, but this term right here of dy prime dt is y double prime e to the t. So if we put a y double prime e to the t here and then distribute this e to the t across, we'll get e to the t y prime right there. Then e to the t times this term would be e to the 2t y double prime right there. So here's what we've determined to be d squared y by dt squared. Now, if we solve this expression for y double prime, we would have to multiply both sides by e to the minus 2t, and then we would need to subtract this term right here. At the end of the day, you'll have that y double prime is e to the minus 2t times d squared y dt squared minus e to the minus t y prime. If we multiply everything by x squared, well, x squared y double prime, remember that x is e to the t. So x squared is e to the 2t. So we're multiplying the entire expression by e to the 2t. That cancels this right here. When I multiply this by e to the 2t, it would just become x, or e to the t. Of course, that second term, xy prime, is exactly dy dt. So x squared y double prime is the same as d squared y dt squared minus dy dt. So from the previous slide, here's an expression we had for d squared y by dt squared, e to the t y prime plus e to the 2t y double prime. We're going to take a t derivative of that. Now we're going to apply the product rule. So we're going to have the derivative of e to the t times y prime unchanged. Of course, d by dt of e to the t is just itself. But we're also going to need e to the t times d by dt of y prime. Similarly, we're going to need two terms from this expression here. Altogether, here's the four terms generated. Now, in order to express d by dt of y prime and d by dt of y double prime. Since y prime is a function of x and y double prime is a function of x, we're going to need the chain rule for these. So what's d by dt of y prime? It would be dy prime dx, which is simply y double prime, times dx dt, and that's e to the t. Similarly, applying the chain rule to d by dt of y double prime, we get dy double prime dx, dx dt, which is just y triple prime times another e to the x, transforming this into e to the 3t. These two terms here both have shared factors of y double prime, e to the 2t, once you express e to the t times e to the t as e to the 2t. So altogether we have 3 e to the 2t y double prime. So here is our expression for d cubed y dt cubed. Solving for y triple prime by multiplying everything by e to the minus 3t and isolating the y triple prime, well, you'll end up with e to the minus 3t times this derivative, there it is. E to the minus 3t times this term would leave behind an e to the minus 2t, then move it to the other side, so it has a minus sign. Similarly, e to the minus 3t times this term moved over to the other side gives me a minus 3 e to the minus t y double prime. In our Euler equation, the term y triple prime was multiplied by x cubed. Now x cubed is e to the 3t. So if I multiply every term here by e to the 3t, this cancels exactly. This leaves behind an e to the t, in other words, an x. This leaves behind an e to the 2t, in other words, an x squared. And we've already determined that xy prime is exactly dy dt, and we've also already determined that x squared y double prime was exactly this difference here, d squared y dt squared minus dy dt. Simplifying everything that results here, we end up with the third derivative of y against t minus 3 times the second derivative plus 2 times the first derivative. And this is an expression for x cubed y triple prime, where y triple prime is the third derivative against x. So far, what have we deduced? xy prime is dy dt. X squared y double prime was the difference of the second derivative of y against t minus the first, and x cubed y triple prime could be written as the third derivative against t minus 3 times the second plus 2 times the first. We're going to simplify our notation a bit. We're going to call capital D the operator d by dt. So what we have here is xy prime is simply dy. X squared y double prime is d squared y minus dy. D squared y minus dy. But that factors as d times d minus 1y. Derivatives are linear operators, so this factoring is totally legitimate. Here we would have d cubed y minus 3d squared y plus 2dy, and that factors as d minus 1, d minus 2 of y. So with capital D as our linear operator, the t derivative, we've got xy prime is dy, x squared y double prime is d minus 1 of y, x cubed y triple prime is d minus 1, d minus 2 of y. So what we could inductively prove is that this pattern does continue. And again, we're omitting the formal proof, having established the first several cases. The nth power of x times the nth derivative of y against x is simply a product of all of these linear operators, d minus 1, d minus 2, all the way to d minus n plus 1, all of that of y. 1 power of x, we ended at d minus 0. 2 powers of x, we ended at d minus 1. 3 powers of x, we ended at d minus 2. So n powers of x and n derivatives, we end at d minus n plus 1. This substitution now replaces all instances of the non-constant coefficients x to the n times the nth derivative, and now we simply have constant coefficients. However, we have our linear operator d, which is the t derivative. So once we've done this substitution, the differential equation has been transformed into one with constant coefficients, and we know how to find solutions to those. We make a characteristic polynomial and factor. Depending on the multiplicity of different real and/or complex roots of this characteristic polynomial, we create a fundamental set of solutions involving terms like e to the at, t e to the at, etc. We may also have exponentials times cosines or sines, and possibly with t's, t-squareds, etc., multiplying those. Once you perform the substitution that x is e to the t, in other words, t is the log of x, these sorts of terms for our fundamental set get replaced with, well, if t is log x, then this becomes x to the a, this becomes x to the a times log x, and so forth. We would also get x to the lambda times the cosine of omega log x. There's no simplification that happens in here. So we would get x to the lambda cosine of omega log x. We would also be able to find things like x to the lambda log x cosine of omega log x, x to the lambda log x squared, etc. And the same thing with sines instead of cosines. Let's take a look at a first example. Find the general solution to x cubed y triple prime plus 3x squared y double prime minus 6xy prime minus 6y equals 0. Note this is a generalized Euler equation. The power of x always matches the number of derivatives of y being taken. We know that when we do the substitution x equals e to the t, we're going to be able to replace x to the I times its matching derivative of y with the product d minus 1 all the way down to d minus I plus 1 of y, where capital D is this t derivative, d by dt. So when we do that on the problem here, x cubed y triple prime becomes d minus 1 d minus 2 of y. This 3 is there, otherwise x squared y double prime becomes d minus 1 of y. The 6 sits right there, otherwise xy prime is just d of y, and the 6y stays where it is. Multiplying everything out, we have d cubed minus 3d squared plus 2d of y, plus 3d squared minus 3d of y, minus 6d of y minus 6y equals 0. Altogether, we have d cubed y plus no d squared y, those canceled out, minus 7d y minus 6y equals 0. In other words, we have the third derivative of y against the variable t minus 7 times the first minus 6y equals 0. So now we have a constant coefficient third degree differential equation. So we make a complementary equation, r cubed minus 7r minus 6, and set that equal to 0. That factors as r plus 1, r plus 2, r minus 3. So the modified differential equation, the one that is now expressed as a function of t, since the roots of its complementary equation are -1, -2, and +3, we have e to the minus t, e to the minus 2t, e to the 3t. There's a fundamental set of solutions to the modified differential equation. So here's our fundamental set of solutions to the modified differential equation. Now we resubstitute that x is e to the t. So we just have x to the minus first, x to the minus second, x cubed. E to the t to the minus 1, e to the t to the minus 2, e to the t cubed. So here is a general solution to the differential equation we started with. C1 times x to the minus first plus C2 times x to the minus second plus C3 times x cubed. For our second example, find a general solution to 8x cubed y triple prime plus 20x squared y double prime plus 2xy prime plus y equals 0. So we do the same substitution. We perform all of the tricks regarding x to the n, y, nth derivative being replaced with a product of linear operators, and we end up with, well, the 8 stays where it is. Otherwise, x cubed y triple prime is d minus 1, d minus 2 of y. X squared y double prime, d minus 1, xy prime, d, y itself. Now we distribute everything out. We'll end up with all of this. And now we just have to collect like terms. And we end up with 8d cubed y minus 4d squared y minus 2dy plus y equals 0. Interpreted as a function of t, this would now have complementary equation 8r cubed minus 4r squared minus 2r plus 1 equals 0. So once we transformed this to be a differential equation with the variable t, we got this complementary equation. Now we simply need to factor. If the equation has any rational roots, they must be of the form plus or minus a factor of 1 over a factor of 8. constant coefficient factor over leading coefficient factor. So we have 8 possible rational roots, plus or minus 1, plus or minus half, plus or minus quarter, plus or minus eighth. Just by actually checking all 8 of these, r equals a half and r equals minus 1/2 are both roots. This eventually allows us to factor the original complementary equation as 8 times r minus a half squared times r plus a half. So the complementary equation was factored like this. A fundamental set of solutions is now given by e to the 1/2 t, t times e to the 1/2 t, because the root of r equals 1/2 had multiplicity 2. And here we get e to the minus t over 2. Now we convert back by replacing x equals e to the t, and we end up with x to the 1/2 log x times x to the 1/2 and x to the minus 1/2. So here is a fundamental set of solutions to the original differential equation. So therefore, a general set of solutions is given by some constant times x to the 1/2, or root x, plus some constant times log x root x, plus some constant times x to the minus 1/2. So here's a general solution to the original differential equation. For our third example, let's find a general solution to this fourth order Euler equation. X to the fourth y fourth derivative minus 2x cubed y third derivative plus 7x squared y second derivative plus xy prime plus 16y equals 0. Well, we know we're going to perform the substitution x equals e to the t, transforming all of these powers of x times derivatives of y into products of the operator d. Specifically, x to the fourth y to the fourth gives us d minus 1, d minus 2, d minus 3 of y. X cubed, third derivative of y, d minus 1, d minus 2. X squared, y second derivative, d minus 1. X, y first derivative, d, nothing here, leave it alone. Now we just have to distribute all of these polynomials in the operator d. We're then going to collect by like powers of d. Eventually, what you would end up with in this problem is d to the fourth y minus 8d cubed y plus 24d squared y minus 16dy plus 16y equals 0. We now have constant coefficients in a differential equation as a function of t, so we make the characteristic polynomial r to the fourth minus 8r cubed plus 24r squared minus 16r plus 16, set it equal to 0, and now we need to factor this fourth degree polynomial. Eventually, applying the rational roots theorem for a head start, we're going to factor this as r minus 2 to the fourth power. So we factored the characteristic equation of the modified differential equation as r minus 2 to the fourth equals 0. Therefore, the fundamental set of solutions is given by e to the 2t, t e to the 2t, t squared, e to the 2t, and t cubed, e to the 2t. But we're going to replace our variable x back into this. E to the 2t is just x squared log x squared log x squared, and x squared log x cubed. So here is a fundamental set of solutions to the original differential equation. So a general solution can be written out as c1x squared plus c2x squared log x plus c3x squared log x squared plus c4x squared log x cubed. All in all, what did we discuss? The same substitution x equals e to the t, which was used to solve second-order Euler equations, can also be used to solve higher-order equations of the same form. After performing that substitution, you get a related differential equation in t, but all the coefficients are now constants. We know how to solve higher-order constant coefficients differential equations, so do that. You'll now have a fundamental set of solutions in terms of the variable t, but convert back to the variable x that you started with. Now you have a fundamental set of solutions to the differential equation you started with. If this was an initial value problem, you could take a general solution and use the initial values to solve for the unknown coefficients. If it were a non-homogeneous equation, you could proceed with variation of parameters. The method of undetermined coefficients wouldn't really be an option here because the differential equation we started with did not have constant coefficients, but variation of parameters would work just fine.